actual bar problems where we need to consider how to represent their strain energy. Okay, so this is the one that I'm going to start off with. And if you look at, again, the notes in this particular page, which it gives another example, which is example 5.3 here. So example 5.3 is actually a truss example. Later I will show on the screen there. Okay, it's actually a truss example where we can then apply the PNPE to solve this problem. So the truss example is an example that we have been using very often. Okay. So we can use PNPE to solve problem like this, which is given in the, so this example, we have used it many times. Okay. And each of them has their own cross-sectional area and also, of course, angle theta 1, theta 2, and so on. So this is the example which is being used again to show you how to solve this problem using principle of PNPE. How to get this using PNPE? One that we want to solve is U and V. Given this loading FU and FV, and given all the cross-sectional area of the bar, and given the geometry of the problems. So this is a problem which is using here in this example. And I just want you to go through that solution process. It is written very clearly in this page here. You can refer to this particular page 183, where they gives you the potential energy of external load. The potential energy of external load class, you have two here. You have a two load here, which is FU and FV. That's why they give us FU and FV. So minus, so that must be a minus FU multiplied with U and minus FV multiplied with V. So this is the potential energy of external load. And the strain energy, these are all bar problem, bar. So the strain energy is given by, for a bar, which is the strain energy for a bar, which cross-sectional area A with modulus of elasticity E with the length L is given by a half these equations here. I hope you refer to your notes because this is not clear here when I show it to you. So it is half AE over L for each of the member multiplied with the elongation square of each of the member. And how many members we have, you add them up together. So this is the strain energy. This is the potential energy of external load. Then here we introduce these equations to make sure that there is a compatibility, because here elongation must be related to U and V. So again, we introduce this equation that we have seen before in order to make sure that all the members still join together. We must satisfy this elongation here, must satisfy this relationship, which we have seen before when we earlier on. Okay, so when this is being considered here, so the strain energy can be expressed in terms of U and V only. So this one introduced into these equations, then we add up this one and this one. So this is the one that we get for total potential energy. So total potential energy, as when it comes to this is a function of u and v. Okay. So class, again, I'm sorry, this is not clear here because the letter is a bit not focused. Please go through again with all these steps here because these are explained very well in this notes here. So what I want you to look at is the final equations. So again, application of P and PE means that you have to differentiate first with U, next with V. So you get two equations, and if you summarize them, finally you get the equilibrium equations. Finally, you get the equilibrium equations that we need to solve this problem. So by applying P and PE, we get the equilibrium equations. This one is given. This one is given as the loading. All this K1, K2, K3 is, we can calculate because K is AE over L. K, this is axial stiffness. Axial stiffness is AE over L. So this one, what we don't know is U and V, U and V. So we need to solve for U and V using these two equilibrium equations for this problem, which is 2 degrees of freedom. Okay. So we get the equilibrium equations using PMPE, okay, without going through the normal way. So application of PMPE actually give us the equilibrium equation, then we can solve for the displacement that we want. So here, what you need to be aware of is how to get the strain energy for bar. Okay, so strain energy for bar is half K. So K is for spring is just K, but for bar is AE over L. Okay? K for bar is A multiplied with E over L is the axial stiffness, and then multiplied with the elongation square. Multiplied with the elongation square. So please take note of these calculations of strain energy here. AE over L is the K. E is the elongation. So K half AE over L multiplied with the elongation square is the strain energy of a bar. Okay. And you have how many bars? You just add up how many bars. So that is one particular problem of application of PNPE, which is given very detailed in this note that you can refer to. Now, I would like to show you another example where look at another example of application of PNPE. Now we all use 1D problem because 1D problem we can solve it, we can still solve it. When we go to 2D, I think it will be very difficult to solve it. But to illustrate the procedures, okay, so I use mainly 1D problem. So I have now, this is a statically indeterminate problem. Okay, you have a bar now, a bar with 3 segments with different lengths. Okay. And each of the bar has different cross-sectional area, different materials. And there is a loading being applied here. This is there is a load applied at this point, which is E1. So this particular problem also, we can solve it using PMPE. Previously, I think if we apply, I think these basic equations that we have in structural mechanics, the equilibrium, stress, strain, and also strain displacement, we can also solve this problem. This is a statically indeterminate problem. Okay? But using PMPE, we can solve this. So here we need to identify what is the degrees of freedom. What is the degrees of freedom that we have for this problem? So for this bar, yeah, if we know what is the displacement here and what is the displacement here, because this is fixed, then we know what is the deformed shape of this bar. So we need to know what is the displacement here and what is the displacement here. So this is 2 degrees of freedom. This is 2 degrees of freedom problem. Okay? And this is statically indeterminate problem. We don't have enough equilibrium equations to solve this. Okay, but we can solve it using PMPE. And we first start by identifying the degrees of freedom, which is U1 and U2. So the next thing is, after you have this, if you want to use PMPE class, you should know how to. If you want to use PMPE, so what is the strain energy for the bar? So in this case, we have 3 bar, which can only move in this direction. So these are all axial deformation problem only. So UP is equal to strain energy in bar number 1 plus strain energy in bar number 2 plus strain energy in bar number 3. Okay? 1, 2, 3, you add them up together. And what is the strain energy for bar? So as I explained to you using the example just now, so this one become half A1 E1 over L1 multiplied with the elongation. And the second one is half A2 E2 over L2, second member. And what is the elongation of this? You can take this as U2 minus U1 square, the elongation. Okay. This one go U2, this one go U1, so the elongation of this is U2 minus U1. Then the last one is A3 E3 over L3 U2 square. Okay. So here in this example, just try to refresh, try to point out to you the strain energy for bar with AE, the length L is half AE over L U1 square. Okay. So this is, the bar is a uniform cross section. If the bar is non-uniform cross section, then we have to integrate. We have to do the integration. This is bar of uniform cross section. Yeah. This is cross section the same all the way, cross section the same. So this divide into 3 parts. So each part, the strain energy is like this. If the bar is not same cross-sectional area, then it's not like that. You have to do integration. If the bar is not the same cross-sections. Then VP class, what is the VP here? What is the VP here? minus V1 U1 minus again P2 U2. This is the Vp. External load is here. So the corresponding displacement at the point of action of this is U1. So this is U2, negative, negative. So this is the. So next you get pi p. You just add up all this, which is I can put this as a summation. I cannot put summation because half A1 E1 L1 E1 square plus half A2 E2 L2 U2 minus U1 square plus half A3 E3 L3 minus P1 U1 minus P2 U2. So after you have this, you just need to differentiate, okay? Okay, you can differentiate this respect to U1 partially, make it equal to 0. The second one partially differentiate respect to this, make it equal to 0. Then that is what we get. And then we get the two equations, okay? You can try to get this, okay? Try to differentiate this class as an exercise for you. You need to differentiate this partially, yeah? Partial differentiations. Respect to U1. And then this respect to U2. Try to, this, I give you the solution here, okay? So from here, you get so this is the resulting two equation that you will get. You should try to get yourself familiarized. I think refresh again partial differentiations and then summarize. You should get this from here, and from this you get this. Okay. So these are the equations that we can solve. P1 is given, P2 is given, K1, K2, K3 are all given because K1 is A1, E1, L1, K2 is A2, E2, L2, and so on. These are all given. P1, P2 given, then you can solve for U1 and U2 here. Okay. So this is another example, which is, I think it is procedure is quite straightforward. Only thing is when we do calculations at the end, when we want to solve this, it is a bit time consuming because this is solving simultaneous equations. Okay. So by now, I think you should be clear. Get UP identify the degrees of freedom. If it's not given to you, get UP, get VP. UP, depending on this, is bending or axial deformation or twisting. This is axial deformation. And what is the UP? Okay. And how to get VP and get pi P. And then after that, PMPE is this, meaning this is this, depending on how many degrees of freedom you have. Then finally, these are the equations to be solved. So those are the steps involved. Now I'm going to give you one example that I want you to try out. Okay. Which is, let me check. Well, I want you to look at this problem and try to get the equilibrium equations. This is fixed here. You have another bar which is located here. And this bar is suspended by two springs here. Okay. And these two springs, the distance between them is 1 meter. And the spring constant is K1 and K2 for this spring. And there is a load acting here, P, and this is acting not at the center, but at certain offset eccentricity from the center. Okay. You're asked to take K1 and K2. So here, class, they get familiar with the units for K1. Axial stiffness is force per unit length. It can be Newton per meter, it can be Newton per millimeter, but it must be force per unit length. Okay. So you derive first the equilibrium equations. Okay. Then after that, you take K1 and K2 equal to 3 kilonewton per meter and P equal to 300 Newton. So values given to you now. And then with this value given, you solve the equations, which means you try to get the displacement, which is degrees of freedom for this problem. Solve the equations, meaning that you have to get the displacement representing this problem and determine the forces in the spring. Determine the forces, yeah? Determine the forces in the spring. So for this problem, with two springs like this, and this is assumed as rigid, okay? This bar assumed as rigid. And use PMPE to derive the equilibrium equation. Derive first in terms of K1, K2, and then P. Then substitute value of K1, K2 is this and this into your equilibrium equation that you derive, and then solve that equations. Then after that, after you solve, you get the displacement representing this problem first, then you get the force. So try to solve this, I think, class. Try to solve this and to familiarize yourself with the procedures that you need to go through if you're asked to solve using PMPE.